Okay, let's do another question like this where we're asked to rationalize the denominator. So we have a square root 5 on the denominator there. So I'll give you a chance to pause the recording here and try to answer this question, and I'll come back in about 10 seconds. Okay, hopefully you've had a chance to answer this question. Now, to rationalize this denominator, we need to get rid of that square root. That's the end goal. So some people may just think that you have to multiply it by the square root side of things. So you may have watched the last lesson a while ago and have forgotten what we're actually supposed to do. But let's just say why we're not multiplying by just the square root 5. Because if we expand that into the denominator, what you're actually doing is, so if I write it out over here, you're multiplying it into every term. So will have a 5 times by square root, or square root 5 times by square root 5. So you're left with a 5. And then you're also going to have plus 1 square root 5. So you're still going to have a square root on the denominator. So by multiplying it with just this, you're not rationalizing that denominator. We rationalize it by multiplying it with the conjugate. So because we have a plus between the two terms, we're multiplying it with the negative. So if we go down and expand this out, so remember, it's kind of like these have their own brackets around it. So we go square root 3 times by square root 5. So square root 3 by 5. We have a square root 3 by negative 1. So negative square root 3, negative 1 by square root 5. So negative square root 5. And then negative 1 by negative 1. So we have plus 1 over. Now we have the first term squared. We have a negative. We have a positive. So the middle two terms are going to cancel each other out. And then we have that last term squared, negative. So you have negative and then 1, 1. So negative 1. So try and expand that out yourself in a couple more steps. Hopefully you get to this as the answer. Remember, we are expanding it out in this form here. So we should be only left with that first term squared minus that second term squared, which is what we have here. The first term squared minus that second term squared. Simplifying the numerator. So 3 times 5 can't really be simplified any further. You have a square root 3 here, you have a square root 5 there, and a whole number there. So I don't think this can really be simplified too much further. So we may as well just combine the square root 3, square root 5. And then on the denominator, you have 5 minus 1, so we just have 4. And that should be the answer for that question. Okay, moving on. Let's now have a look at radical signs. So what we've seen so far is that our normal square roots look something like this, and that was equal to 5 to the power of a half. What a radical sign is, it's a higher order square root. So for instance, if we had the cubed root of 27, say with the normal square root, you're asking what times by itself will give you that number. When you got this higher order, so in this case, the cubed root, what times by itself, 3 times, will give you 27. And so we can see that 9 times by 3 is 27, but that's also 3 times by 3 times by 3. So we have 27 equal to 3 cubed. Now all of this is still within the cubed root. So what that is saying is, if we get rid of this cubed root and bring that into the power, we have 3 to the power of 3 over 3, which is just equal to 3. So the cubed root of 27 is equal to 3. So again, what times by itself? 3 times. Or you might have something even higher. And let's say you have the fourth root of, let's say, 16. So hopefully you can see that the only thing that will be timesing by itself 4 times, uh, well, if 3 times by itself 3 times already gets you up to 27, the number's got to be less than 3. So hopefully, see there's going to be 2. So let's double check. So you have 2 times by 2 gives us 4, times by 2 gives us 8, times by 2 gives us 16. So we have 2 to the power of 4. Bringing that 4 in as a power. We have 2 to the power of 4 over 4, which equals 2. So these are radical signs. Now, if we were to use these radical signs in, say, a question related to surds, let's look at, say, for instance, the cubed root of 27 m9 n 15. So have a go at doing this question. I'll pause it here. I'll come back in about 10 seconds. Okay, hopefully you've had a go at simplifying this. So the first step might be to just bring in that as the power for every one of these terms. So that's equal to 27 to a power of a third, m 9 over 3, n 15 over 3. And then we might be simplifying these easier parts first. So you might say 27 to the power of a third, m 9 divided by 3 is 3, then n 15 divided by 3 is 5. And we saw in the previous part that 27 is actually 3 cubed. So you could have 3 cubed all to the power of a third. Continuing this on, we have 3 to the power of 3. Now, when you have a power of a power, hopefully you remember your index laws. So a power of a power is the same as multiplying. So we have 3 to the power of 3 over 3, m 3, n 5. So 3 over 3 is just 1. So we have 3 m cubed n to the power of 5. That would be our answer for that. Simplifying this radical surd. Okay, next question. We have this radical sign. Let's try and simplify this question. So I have the cubed root of 81 times 27 all divided by 3 to the power of 4. And that 3 to the 4 is within this cubed root. Now, I want you to do this tech-free. Give it a go, and we'll come back to it in about 10 seconds. Pause the video here to have a go. Okay, so coming back to this question. Now, you can try to bring this power into each one of these terms. But let's see if we can just simplify some stuff here first. So 81 and 27 both seem like they could be powers of 3 or have factors of 3 in them. So we could break it up. So 27 is equal to 3 times by 9, which is 3 cubed. Yep. And 81 is 9 squared. Well, 9 is 3 squared. So 3 squared squared is 4. So we have 3 to the power of 4 is 81. So we could actually put this in here. So we have this is equal to the cubed root of 3 to the power of 4 times by 3 to the power of 3 all over 3 to the power of 4. So even before getting to the index laws and adding and subtracting, because we have times and divide, we see that on the numerator here, we have a 3 to the 4, and on the denominator, we have a 3 to the 4, so we just simplify that. So this simplifies down to the cubed root of 3 cubed, which is 3 to the power of 3 over 3, which is just 3. So using just index laws and index notation, we can bring something like this, do it tech-free, this radical sign, down to a whole number. Okay, here's our next question. A bit harder now. So again, we have a radical sign. We're dividing it by another square root. The aim of the game is to rationalize and simplify it. And I'm even giving you the answer for this one. So this would be represented as maybe a proof-based question. Prove that this simplifies to this. So have a go at it, pause the video here, and again, I'll come back in about 10 seconds and we'll go through it then. Okay, hopefully you were able to get to the end answer to prove that this was indeed true. Let's go through and see how you would do that. So there are probably a couple ways that you could go about doing the first step. You could say rationalize the denominator by timesing this on both the top and the bottom, but that's going to get, I think, a bit messy. So instead, let's apply some critical thinking on maths to see if we can do this without taking unnecessary steps. So what I would suggest first is potentially bringing these in as fractions to powers and see how that simplifies. So looking at the left-hand side, we have x, bring the 4 in as a denominator of power. We have 8 on 4, y 6 on 4 over x squared on 2, y 5 on 2. So all of a sudden, this is becoming kind of like an index question, simplifying indices. Now you have division here. Hopefully you can remember that when you're dividing, the powers get subtracted. We have x. Actually, we probably don't need to do the subtraction straight away because this divides into a whole number. This divides into a whole number. So this 8 divided by 4 is 2. So you're going to have x squared on the top, and you're going to have x on the denominator. And then the y's, you're going to have y 6 over 4 minus 5 over 2. So all of this is the power for that y. Now you're subtracting fractions. So let's actually do this part over here separate. So we have 6 over 4 minus 5 over 2. When you're dealing with a fraction, you need to get a common denominator. It's kind of like saying if you have half a pizza and a quarter of a pizza, how do you combine them? Well, you know that just from that example, you probably have 3/4 of a pizza. Well, in that answer, you can see that you've got a common denominator. To get 3/4, that half is broken down into 2/4. So you need a common denominator to get an answer when dealing with fractions in terms of addition or subtraction. So let's bring it all up to a common denominator of 4. So we have 6 over 4 minus 10 over 4. So I've times the top by 2, the bottom by 2. So again, when you times it by 2 over 2, you're not actually changing the value, you're just changing the representation because this is equal to 1. So So 6 minus 10 is equal to negative 4 on 4. So going back to the question, we have x squared on x times by y, negative 4 on 4. And 4 on 4, let's just say that's negative. Just put that in as a negative 1. So y to the power of negative 1. So we have x squared minus x to the power of 1. So it's going to be 2 minus 1. So let's just have it as x, y to negative 1. Now, what is meant by negative in the power? So let's just go through and try and explain what's happening there, seeing as we want to give our answer as positive indices. Now, I'm just going to take a side step here to explain this, and then we'll come back to that question. Let's say you've got your tens columns back from primary school. You had like your ones, your tens, your hundreds, your tenths. Now, if we just pick a number, let's say 5, we're representing it in ones. It's 5 and tens, we might say 50, and hundreds might say 500, and tenths we'll put it as 0.5. It's the same number, but different order of magnitude. Now, writing this in scientific notation, something that you should have seen maybe a year or so ago, we have 5 by 10 to the power of 0, because 10 to the power of 0 is a 1. For 50, that'd be like 5 by 10. So we'll represent that as 10 to the power of 1. 500, let's go 5 by 10 to the power of 2, because it's 5 times by 100. And then for 0.5, that's the same as saying, well, if we just go off these patterns, we have 2, 1, 0. So this would be negative 1. So 5 by 10 to the negative 1. Now, 0.5, another way that you can get that is by saying 5 divided by 10. Give it a power of 1. So we have this in scientific notation is 5 by 10 to the negative 1. But in this form, we have a positive power, but it's on the denominator. So really, it's kind of like saying the taking it from 1, either the denominator to numerator or numerator to denominator, you can change the sign in the power. So we have a positive here, we bring it up to the numerator, it becomes a negative. So we can go over a quick example as to why that's the case. So let's just say if I have the number 1 over 5 all to the power of negative 2, for instance. If you type this into your calculator, hopefully you get the number 25. So just type that into your calculator, just confirm that that comes out as 25. I'll give you a couple of seconds to pause the video here so you can do that. Okay, so continuing on, let's see how we would do this. Well, you bring the negative power into each individual term. So you have 1 to the negative 2 over 5 to the negative 2. Now you're dealing with the negatives. So the 1 can have a positive indice on the denominator, and the 5 can have a positive indice on the numerator. So we have 5 to the positive 2 on the top, 1 to the positive 2 on the bottom. Anything over 1 squared, well, 1 squared is 1, so anything over 1 is 1. So that is now just equal to 25. So a little bit of a side step, but that's what the negative powers mean. Again, that should have been taught in year 10, but it's nice to just to revisit these topics when we need them in this current topic. So finishing off this question, we have negative power in the 1. So it'll be equal to x over y, which is the end answer that we're asked to prove. So therefore, left-hand side equals right-hand side. And that's the end of that question.